Thanks, Christine. Thanks for joining everyone for this webinar to discuss the remote dust monitoring application for the micropulse LiDAR or mini MPL product line. So really, there are three main reasons why our kind of mining and industrial customers might talk to us. So generally speaking, those fall into the buckets of health and safety. If there is some particulate emission which might have a heavy PM10 content, or maybe of a material that could be damaging to mine personnel, or if you have a complex operation with lots going on and there are, that's constantly changing and is maybe affected by photography and weather, or if you have the angry neighbor problem. So a facility or an operation that is located near to a population center or is near to an alternate operation. Those will be reasons to think about adding remote sensing to your dust monitoring and mitigation strategy. If you are in an area that's close to an urban point, then you have to think about your license to mine. You have to think about the fact that the regulatory bodies may be more engaged with your activities, and the local population is very much going to be aware of what's going on in and around your mine. So there are really four areas where we think the remote dust monitoring solution based on mini MPL can have an impact in your life of your operations. So the first of those is in the planning piece. So how dust moves around operations is a problem in general, right? So particularly in a mine, operations throw up a lot of dust, they have to be mitigated. So how it moves around is not a trivial thing to understand. If you can add the remote dust monitoring to your mitigation strategy, then it's going to give the operations folks an understanding of how things move, which can be used for modeling activities in the environmental group. If you're thinking about your emissions, it can be used for planning activities, can be used for scheduling, and allow you to be pre-prepared ahead of weather forecast, understanding what the dust movement within your site is going to be. The next level is really controls, right? So having a good hand on your emission source, so you can think about your long-term abatement strategy, and also be able to consider implementation of short-term mitigations if those are needed. So because the remote dust monitor system gives you an overall mine picture, it's a piece of the puzzle that otherwise wouldn't exist, right? It gives you a view that really can potentially allow you to connect up all the dots of what's going in your operation. So rather than having several sensors on their own spread about that aren't necessarily linked up to each other and thus can be overlaid in your operations, this essentially is allowing you to tie a lot of things together. Thinking about the management side of things, we believe that, again, having a more of a site-wide picture of what's going on will allow you to think about trends. And so you might have an expected kind of background emission level, and this would allow you to understand if anything new is happening out of the ordinary. Or it would allow you to, yes, so there's a question just come in. So yes, essentially, if you have an activity for your mitigation, such as using water cannons or watering areas down, a total picture of what's scanning over a mine, when your large trucks are moving through, or what's blowing off your tailings, you start to see dust signatures in a region where you wouldn't expect it to, or you start to find a hotspot. that'd be an application that the remote sensing would provide you. And then again, on the investigation side, so you're going to get a historical picture of what's been happening in the operations. So you can do some root cause analysis and look for your hotspots and really understand what's happened with a view to predicting what may happen in the future. So I broke this quick presentation down into 4 chunks, right? So a little bit of the heritage of micropulse LiDAR just as a division. Talk about the core product this technology is built around. I'll talk about the measurement, assuming that you're somewhat unfamiliar with LiDAR, and I'll try and tie it back to how it's useful to this type of application. And then some case studies. I would say 2 which are directly applicable to the motion of particulate that's picked up, and 1 that is a demonstration of the power of the instrument when linked up with kind of other technology for a kind of an alert response system. So a little bit about micropulse LiDAR. So we have about 160 installations worldwide. I believe if you go through Google Scholar, you'll probably be able to find about 1,000 publications that have been put together using MPL or mini MPL products. So it's a widely used and researched bit of equipment with government and academic research labs. We've been putting a lot of time and effort into making a technology that is robust and allowing us to really think about how this data is presented so that the information can be operationalized and used in mining operations or an operational concern, where the concern is less the detail of the data that you might get from a NASA product and more about the decisions that can be made with that technology. But just referencing NASA a little bit more before I move on, we are the sole supplier to their global network of cloud and aerosol monitoring sites. It's called MPLNet. You can Google it, go online, and have a look at the back catalog of data, what's happening. So basically, anywhere in the world at some point, there is one of our systems measuring the atmosphere above you. So it's quite widely deployed and has been there for a long time. And we do hold the distinction of being the only technology from a LiDAR meteorological point of view that is used in EU MetNet and also used in NASA's MPLNet. So that is a fairly unique distinction there, and it talks to not only the quality of the instrument, but also the commitment of the user community that stands behind it, because they're really the people that do the evaluation and drive it forward and have the feedback into kind of continually improve the technology. So shout out has to go really to the customers, because they've really made all this happen. So thinking about the instrument itself, what is the core technology that is making up the remote dust monitoring application? It's built around this little box called a mini MPL. So the mini MPL box is a small bit of equipment. It weighs about 13 kilos. It's roughly the size of a desktop computer. It's got a very low size, weight, and power requirement. And coupled with that, it's available in 2 wavelengths of 532. So it's a laser-based instrument. It's got a green laser emission source, or it's got an infrared laser emission source. So one is a visible beam, one is an invisible beam. It's a class 2 laser product, but it is eye safe right at the aperture. So it's totally safe from that point of view. It is built around a very rigid internal mechanical structure, which makes it a very stable instrument. It was designed with a view to being able to put them in lots of different locations and integrate them very easily into lots of different applications. So we'll show you some examples of that. And its whole data quality model is built on this efficient photon management concept. So it's a LiDAR instrument. It's a time of flight instrument. So it's sending out laser pulses, and it is essentially counting the photons that are backscattered from the atmosphere. So that's essentially how it works. And we have a model that uses a very low power laser coupled with extremely efficient photon detection. So that is a unique thing about our particular LiDAR equipment versus other ones you might find. And the last one is really about the ethos for us, right? So I've mentioned integration once before. This is true in the hardware, in that it's small, it's got low power consumption, it's a very nicely self-contained unit. It's also true in our software. So our software is designed to be fairly modular, so that we can integrate third-party instruments into our own display software we want to. And it's also designed to export our data profiles so that those can be viewed through, we have another web-based viewing tool, which is multi-tenant, or you can input that data into some other system. So that would be something that we'd work with you on. So as you can see, it's a unique core little box here. And thinking about it as DNA, it shares component history with several fairly high-profile NASA missions. So we tried to show this schematically here, right? So on the top of your screen, you can see space missions, Calypso, ISAT, ISAT-2. So these are some pretty famous missions. So ISAT is measuring the heights, the elevation of your polar ice caps, and Calypso is an aerosol LiDAR style. So we are sharing photon counting, detection, and optical filtering with those technology platforms, as well as the cloud physics LiDAR, which is a near space mission. That's a drone, flies around the world at 60,000 feet, measuring the atmosphere with LiDAR and radar. So we share photon counting and optical filtering with those technology platforms. It shows you where the data quality is coming from. The simple mission also used similar photon counting, and we spun out of a company called Sigma Space. And Sigma Space was a participant in the Twilight mission and developed some of the MCS timing cards and technology for that. And that technology is baked into the Mini MPL and the MPL platforms as well. So you can see we've got kind of a heritage of doing some pretty sensitive, pretty high-tech stuff. And there's a bit of an aerospace heritage there for the MPL technology as well. So you can see that it's kind of tried and true, has tested and well vetted. I said before that we focus somewhat on making it able to be integrated in multiple platforms. So this slide is a nice one because it shows you some of the different projects and missions that we've been a part of. So the Mini MPL is kind of at the center. To the left is our standard system, if you will. That's our enclosure and our scanner. So that's the topography of the remote dust scanning system. To the far left is a smaller tank enclosure that was done for the US EPA and the Navy. That actually is sitting in a shipyard in somewhere I can't tell you, that is essentially looking at the opacity of the plume that's coming off from metal cutting operations. So if the plume's too dark, that means the chemical rubber compound and the metal being cut is too high, and it's an emission operation that needs to stop. So the ability to actually give you a quantitative measure of plume opacity, while not a particular of this webinar, is also another feature of this technology. The bottom left, you can see it poking out the side of a window. So that is actually an aircraft at Bariloche Airport in Argentina. So they fly the instrument and they fly it through clouds, and they're looking at the volcanic ash content of clouds as they're flying the aircraft. Below that is another airborne deployment. I didn't have actual photos of it, but you can see that's done to shoot vertically up and down to giving you total column. Top right is a car roof type deployment, and then the bottom right is the deck of a polar research vessel. So this is a Korean Polar Research Institute icebreaker vessel. You can see that essentially the system has a vibration mount internally and is bolted to another vibration mount. So again, just reiterating, air, land, and sea, we're kind of covering it all. So what's the topology of the system? So Mini MPL is the core. It has a laptop that's driving it on the right, and that fits inside our doghouse enclosure that has a scanner on the top. So the scanner, of course, is optional. You can shoot straight up through the atmosphere. This enclosure itself is essentially goes on a platform and is anchored to the ground. If there's additional vibration needed, we have a vibration mount that can wrap around the mini MPL and go in the enclosure. There is also a vibration mount if the mini MPL, for example, was going to ride inside your car, which is what JPL do. They essentially just put it in their car and shoot it through the sunroof. So there's a lot of versatility there, because when the mini MPL is on its own, you can run it off a cigarette lighter in a car, just to give you an idea of the power requirement. So a little bit more about the technology itself. The LiDAR is, as I said, green laser or infrared, eye safe right out of the aperture, and it has a maximum range of 15 kilometers if you're shooting vertically. So that's an important number. If you shoot vertically, you can see 15 kilometers, and if you shoot horizontally, due to the thickness of the low-level atmosphere, that drops to about 6 kilometers. So that takes me on to the measurement itself. So what I'm going to do is I'm going to start from the raw signal and kind of build you up so you can get an idea of what it looks like. So this is a nice schematic of a vertical airfoil profile. So it's raw data on the left with an image representation of what you might be seeing. So the LiDAR shoots pulses of photons every at 2500 hertz. And once the laser fires, that triggers the clock. The photons shoot up, they backscatter off the atmosphere, and then we essentially count the returns. And we use the time that it took them to go out, bounce, and come back to give us an idea of the range. One of the other unique bits of our equipment is that it actually shoots in cross and co-polarized states. And that's significant because they scatter off the aerosol differently depending on the shape of that aerosol. So what we're able to do is take that from these two cross and co measurements, actually take a depolarization ratio of those two and use that to help us have an understanding of what the particles are in the atmosphere above us. So essentially, we're figuring out what's up there based on the shape of the aerosol itself. We're able to give profiles from 1 second up to every 30 minutes, and from a range resolution of 5 meter bins up to 75 meter bins. So there's quite a high temporal and spatial resolution that's available with this system. And just looking at what we're seeing here, if we go about 2 kilometer height, right? So that's range on the y-axis. You can see a big green spike down on what we're looking at is essentially maybe a cumulus cloud. So a big green spike, but nothing happening in red means essentially there's a lot of water, right? Lots of kind of circular aerosol droplets collected at that point in the atmosphere. That drops off as you go, and then up at about 10 kilometers, we can see multiple spikes in the red and spikes in the green. So the cirrocumulus and cirrostratus clouds up there are showing us to be much more highly depolarizing. So, at 10 kilometers up, we're probably thinking very cold, so lots of ice crystals in the cloud, those kind of features. So already there's quite a lot of information we're able to bake out based on these kind of two simple bits of data. Then what we do is we take those profiles and we stack them by time. And we apply a false color for the intensity on top of that. And that gives us our typical LiDAR picture snapshot of the atmosphere. So instead of seeing the kind of photon counts as a peak, you now see it as a color. So the more returns, the hotter the color, less returns, the cooler the color. Then on the bottom axis, you've got time. So now you've got a really kind of detailed picture of the atmosphere unfolding. So how is that potentially used, right? So because the instrument's very sensitive, we're seeing a lot of particulate information in the atmosphere. One of the features that we have is the ability to quickly and accurately and pretty reliably detect the planetary boundary layer in the atmosphere. So anyone who is looking at urban air quality needs to have an understanding of their industrial emissions, or has any kind of environmental modeling component to the work they do. And there are quite a few, regionally mines that we talk to where this is an important component, right? You need to know your planetary boundary layer. That's the layer that essentially caps the atmosphere where a lot of your pollution collects. So the higher the PBL, that's going to affect the low-level particulate transfer, or the lower it is, the worse the air quality for you. And as you go through a day, as the day heats up, as the operations run, and the more pollution collects, and et cetera, and the more emissions there are, it's going to be an important factor. So that's an important product that you get. One of the examples you get out of this product. Another really interesting view is our particulate type. So I said earlier that if you took the ratio of the cross, and the copole, you're able to essentially look at how depolarizing particles are. There has been a lot of research done all over the world using this style of LiDAR and calculating out what exactly in certain conditions the dipole ratio corresponds to in terms of particles. So based on that data, we're able to essentially apply a false color on top of that, so that we can tell you operationally, okay, you are looking at a band of dust, you are looking at water clouds, you're looking at polluted aerosol, clean aerosol. So we work with our customers will be able to work with the software in the system to potentially tweak the names and the buckets for their region, depending on what exactly they are kind of looking for, and what the important particle type they're controlling for is. But we essentially give them the tools to be able to do that. And right out of the box, you can see that it makes a big difference, right? So you can see a strong dust band surrounded by fairly clean aerosol above and below it, with some low-level pollution visible. So this is taken on the mountain in Potenza in Italy as part of a campaign that we participated in at that point. So we know that red band is sub-Saharan dust that blows through periodically in southern Italy. So we're very confident in what we're seeing in these graphs. So taking a step back, four of the kind of main buckets of aerosol that we do a very good job of classifying, simply because their dipole ratios are distinctive enough for us to be able to do that. You've got pollen on the top left. So if you are looking at urban air quality, say Barcelona, for example, then you're going to have a lot of pollen. That's something that you're going to really have to pay attention to. If you're in an area with a lot of smog, this is a technology that could be really helpful to you. Mineral dust from blast monitoring events from mining, the particulate that comes off different types of stacks. That's an important thing we can pick up. And then, of course, you've got your high-level volcanic ash. So those little flying swords that destroy jet engines. That's something that can be picked up quite distinctively with this system. So, I haven't talked about burnt biomass. That kind of falls generally into smog. I haven't talked about some of the other particle types that are pretty distinctive. I wanted to focus on ones that could potentially be relevant here. So let's look at mineral dust. So mineral dust, as we said earlier, has a very strong signature. So this is taking another look at a copole and a dipole ratio chart from the LiDAR. So the LiDAR is shooting vertically. So you can see on the left-hand side, I've got 15 kilometers of range, and then it's 3 days of data that's being played through here. So there's a lot of information packed into the screen right now. The thing I'd like you to focus on is really what I'm highlighting here with the mineral dust picture. You can see that the more depolarizing the returns, the hotter the colors get. So it's really picked out very distinctly. And what's interesting here is I'm showing you copol and dipole ratio, and you can see once we put the dipole ratio, that banding really pops out from the background. It's an important point that we've actually, I don't have the case study handy, but this technology has been used by a mine to show that an emission source did not come from their boundary, but actually came from somewhere else. There was a slightly different dipole ratio in the measurement that was being given, but also the hotspot source emission start point was different for each one. So that was something that having the scanning system available provided that information that wasn't there previously. So now I'm showing you that particle type screen again, right? So this, I would call this somewhat an operational view, right? So that heavy orange band that was then false colored directly in our software, and you get that bright red dust signature that's very obvious and is popping out. So that's great. The next thing we'd want to do is really think about what that looks like in terms of the operational map. So this is now a whole, instead of just looking vertically, this is a mine site with a scanning system down at in the dot at the kind of bottom central area that's scanning a wide fan over an operation, and we're showing the false color plot for the particle types identified. So now an operational person that was looking at this will be able to play this backwards and forwards and really see the evolution of the dust pattern backwards and forwards in time within their operation. This is actually just one system, but typically a mine site is a lot bigger. There's a lot more ground they want to cover. Our horizontal maximum range is 6 kilometers. It can vary a little bit depending on weather conditions and time of day, etc. So it's highly likely that for a mine area, you might be thinking about having 2 or 3 of these to support the 50 or 60 other sensors that you're going to have around your site. So this is also being developed to be viewed in a facility that lets you put all of your scanning LiDAR into the same view. So this screenshot is actually taken from a new version of our web dashboard that's available. So there are multiple sites on this site, and the map is actually on an ortho directly from the client. It's not a Google map. So if you have any kind of operations, you know that your Google Maps kind of outdated and not that helpful. So these sites are sitting on the real-time ortho. You can see on the bottom left that there's a little scroll bar for moving backwards and forwards in time, so the operations can see what's happened. I think we can show roughly a week of what's been going on, and you can see on the top right, you can see the current time that's being shown and the details of what's happening in each scan profile for each system. And then, of course, you can see a lot of information here about the particle types, where they're coming and where they're going. So it's a pretty powerful view. In terms of the roadmap here, the intent would be more systems, PM10 monitoring on there, and an ability to really click anywhere that you want and get a view. These systems happen to have our All-Sky 360 cameras on them too. So if you click on a profile, you also get a sky view of what was happening when the LiDAR was taking a measurement. So that's sometimes an important thing that someone might want to get access to. So I want to run you through 3 other examples, right? So we've kind of looked at the instrument, we've taken the measurement and built it up so you can kind of get a feel for what you're looking at, and then we've showed you an operational deployment of how it's being used right now. So here are some other historical cases that could be of interest. So The first one we're going to touch on is looking at the dust particulate emissions from road construction. So in this scenario, there was construction taking place next to a building where we had a scanning system on the roof. The system was essentially just sweeping over the area, taking profiles. Each profile was every 30 seconds, so they're quite high detail profiles with a new scan happening every 5 degrees. And you can see how the dust plume is evolving from 0 minutes to 42 minutes to 84 minutes. So I took random snapshots, but essentially you can see after 0 minutes, there is straight away there's a strong plume emission. Then we can see it this 42 minutes is still throwing dust up and it's dissipating and starting to spread out. And after 84 minutes, you can see again that the same operation is now throwing dust that's heading a kind of northerly direction and an easterly direction. So obviously there's been a shift in the wind or something, or there's some complexity in the atmosphere, but you can see that the dust is not behaving in a simple way, because atmospheres is complex. So you need a strategy to get ahead of that. Now this is a really interesting one. So this is the scanning system used as part of an open path boundary monitoring project we participated in Australia. And what you're seeing here is a site-wide dust motion map that was produced by the customer. So this is something that the customer is essentially using the scanning system for. It's a semi-permanent installation on a trailer that they tend to move around. But when it's placed at this point, they're scanning over the blast zone area. What this customer also uses is the mass concentration feature of the system. So one of the cool things about LiDAR is you can take the total extinction measurement and you can actually calculate an estimate of the mass concentration of the particle along the line of sight of the beam. So you can essentially shoot 6 kilometers away and give back an estimate of what the particulate loading is at that point. So just that's kind of amazing to me that you can do that. So what this customer does is scans the LiDAR over a couple of PM10 particle counters and uses that information to essentially internally calibrate the LiDAR to the point where rather than just reporting our intensity, they actually report the PM10 in micrograms per meters cubed. We have a mass concentration product built into our software. What this customer did was kind of take that really to the next level. And so now they're at the point where working with them, we're able to essentially scan over the mine operations and report all the data back to them in terms of PM10, which is pretty huge for what they're trying to do. So, and the other thing that they're able to do is look at this in somewhat video format. So this is produced post-processing, but I took some screenshots essentially from the video. But what you can see is there's a blast event. So I think I'm showing 119. So about 4 minutes before that, 5 minutes before that, there's a blast event. So you can see this hefty PM10 concentration kind of in the center and heading off west in your screen. And there's some particulates on the right-hand side that are kind of fanning out and dissipating around. About 5 minutes later that, so this is a screenshot of the same one that was overlaid on the map previously. So you can see this larger PM10 concentration. It's slowly expanding and dissipating. And then just 5 minutes after that, we can see that it's moved out of the field of the LiDAR. So it's either settled out or just dissipated, or the cloud has kind of moved through the field of view. But we can see even as long as 20 more minutes after that, at nearly 2 o'clock, you've got these two hotspot regions with PM10 where particulate dust is kind of hanging around in the atmosphere, and that is something that the mine site didn't really have any evidence of before. You know, you could someone could be there and walk through it and see it, but it's not necessarily something that would be operational, right, for them. Now they have this kind of built into the system, and they're able to historically look at what happened. And in terms of how they could use that, that can be used to make predictions about what's going to happen in other blast events, or, you know, if other trucks move through certain parts of the mine. So it's quite a powerful tool that they're going to have at that point. And, you know, just some comments from the practice leader of Pacific Environment, right? So it really was clear that there was a level of monitoring that the managers and the operators had at their disposal that without the system just wasn't anything they had a handle on before. And so the final one is this is a little bit kind of out there. It's not a specifically mining focus, but the reason I have it in this presentation is I've talked to multiple mines about this actually, and this has been something that for them has been quite interesting as a way to think about it, right? So the Pentagon estimates, interestingly, that when there's a chemical warfare attack, there's about 9 seconds for the response forces to suit up and get kind of ready to deal with it. So the idea here was coming up with some kind of long remote sensing threat response system. So what they did was they got an IR camera, a long range one that scans over an area. When it sees some kind of emission, so for example, if this was your mine, that could be a dust plume, it essentially identifies that and then calls into response to the second tier. The second tier in this case is scanning LiDAR. So the scanning LiDAR is directed over the plume and essentially maps the entire emission. Tells you how big it is, what direction it's going, and as it's mapping it, it's also identifying it, right? Is it liquid? Is it a gas cloud? Is it particles? Where's it going? And then it sends those coordinates to threat level 3, which is a drone. In this case, the drone is loaded with instruments, so that you might have a drone that's got particle counters on it. You might want to chase that plume. So I was recently talking at a particle and odor management conference in Toronto, and there were several mine folks there, and they were talking about chasing the plume and being able to fly drones and sensors through it. And this was the concept that we were kind of talking about with those guys. So in this project, what was the output? Really, it was the partner developed this controller view, right? So they had the mind map with the LiDAR at the apex point of that wedge. They're showing you the area that is scanning over, and it can show you the plumes detected and mapped. So that's dictated here by the small green area inside the yellow box. And then on the bottom, you can see the elevation that it's scanning at and the angle that it's scanning. And in these cases, they were able to, it took them, 10 or 11 seconds to map that entire emission source. And then they were able to track it for, 4 or 5 minutes as it moved and spread, depending on the wind, out to about 3 or 4 kilometers. So during that time, they're essentially feeding coordinates to a drone, which is flying through. So it's really an interesting and powerful bit of kit from that point of view. So this one to me is cool because it really plays into what we're trying to do here, right? Like what we're doing is trying to take our users from the left-hand scenario to the right-hand scenario, right? You've got a mine problem, you've got mitigation in place, you're already spending money on doing it, but you might have reached some limitations on how well you're able to mitigate, or you might still be getting events that you're kind of shocked by or unaware of, or you just are struggling to get a handle of it, and the regulators are somewhat breathing down your neck. And maintaining your license to mine is super important, and really understanding if the emission source is you or someone else, or if it's even real. Maybe it's just a water cloud. These things are all important. So the idea here is by adding the remote sensing into the strategy that you already have, gives you the ability to tie everything together. And in the future, in terms of future proofing, when you start rolling in your models, when you start trying to do kind of more advanced operational control, the building blocks are all there to allow you to do it. So it's really, it's really an interesting thing. And in terms of a question just came in about estimating the PM10. So there's a reference. The ACARP project that we referenced has a detailed section about how they did the PM10 estimation based on the LiDAR measurement. So we'll make sure that you get that reference at the end of this. So if you are interested in learning even more, if you go to www.micropulselidar.com, you will find in our case study and blog lots of information about lots of different application areas where micropulse LiDAR technology is being used, and where this this remote dust monitoring application could have value. And we are always here kind of working with your technical teams, and our view here is to get you the solution you need to kind of meet your mitigation and abatement goals. So finally, I'll just leave you with my contact details, and just that leaves me just to say thank you for your attention, and yeah, we'll hope to hear from you soon.